So many people are interested in category theory. This is a new thing. A few years ago, nobody wanted to listen about category theory, and now it seems like it's a very hot topic. Lots of talks, and people are mentioning categorical terms in all the talks. I listened to several talks, and there was like functors, monads, applicatives, all this beautiful stuff from category theory. And also a lot of people talk, when they talk about data structures, they say, okay, things like algebraic data structures, sum types, product types, and so on. All this stuff has roots in category theory. So I want to talk about these things as well today. This is just an intro to category theory, so I won't cover a lot. Here's the plan for the talk. I'll talk a little bit about categorical semantics, about the semantics of programming languages in very generic terms. And of course, I'll talk about composability, because composability is what category theory is about. Then I'll talk a little bit about algebraic data types. Actually, quite a bit about algebraic data types, come to think of it, because it's like a very important part. And then I'll talk about function types, because we're at a functional conference, functional programming conference, right? So function types and currying. And finally, I want to end up with the Monoidal lemma, which is like the central theorem in category theory. So, well, let me start immediately, because we don't have that much time. So, I want to motivate you a little bit, right? And I have lots of motivations why category theory is important and so on. But I think that, like, the real reason why I got into category theory is because it's fun. It's interesting, and it's mind expanding. So if you are looking for reasons to study category theory, maybe you should just like enjoy it. I know that category theory is a branch of mathematics, and a lot of people have some preconceptions about what mathematics is, and a lot of people don't like mathematics because they were starting with primary school, we are like taught not to like mathematics, and here I give an example of the things that we teach our kids in schools. You know, this is like multiplying two numbers. This is a horrible thing. This is like mind-breaking for humans. Okay. There is this huge discrepancy between, or impedance mismatch, as I call it, between human mind and computers, okay? And there are two ways of bridging this gap. One is we insist on being humans and just ask the computers to come up to our level. And the other is to lower ourselves to the level of computers, and I think this is wrong. So this is an example of multiplication, right? We teach our kids to do this, and it has all the elements at which computers are very good and humans are very bad, okay? The only thing that's important here is that there is an algorithm behind it, right? But we don't even tell the kids that there is an algorithm. We just tell them, here are instructions. Perform these instructions, one after another. Okay? And this is the moment where we are teaching kids imperative programming. And they are spoiled for life. And then we have to take years and years to unteach them. You know, functional programming is like the declarative way of saying things. That's much more human. But we are so used to this kind of thinking, the imperative thinking, from the very beginning, that it's very hard to break these things. So here I match things that we are good at versus what the computers are good at. Computers are very very kind of local thinking, right? They look at the next instruction. They are not. They don't have this global perspective that the humans have, right? When we start programming, right? We think about the problem that we are trying to solve. We have this global view, like where does this problem fit into the bigger picture of we want our company to make money, for instance, goals that we have, and so on. So we have this global view, and then we kind of descend to the nitty-gritty eventually, right? Computers are just nitty-gritty from the very beginning and all the time, right? They look at the particular instructions. Computers are progress-oriented. They just want to make progress. They just want to go from one instruction to the next instruction, one line of code to another line of code, and so on. They are not interested in what's happening. It's just locally and making progress. That's important. Whereas we are goal-oriented. We know why we are doing this, right? We have a goal. We want to calculate some value, or we want to draw something. We want to animate some pictures, all this stuff. That's our goal. Making progress for the sake of progress makes no sense for us, right? For a computer, there is no goal. It's just making progress. Computers are very detail-oriented, whereas we operate with ideas. We have these abstractions. We have ideas. We try to convey these ideas to the computer so that it can be executed in some way. Computers have vast memory, right? They have memory in the computer. They can access disks. They can go on the internet, servers, farms, and so on. There's vast amounts of memory. We humans are tiny memory, right? Especially the working memory. We remember stuff from our childhood and so on, but like the working memory is tiny. We can only keep in our working memory like 7 things at a time, right? Computers are pretty reliable. I wanted to write reliable, but then I thought, okay, yeah, right. Computers are made by humans, therefore they cannot be 100% reliable. But when you are writing a program and it doesn't work, your first thought is not, oh, there must be something wrong with the chip, right? Or the compiler has a bug. No, the first thought is, I made a mistake, right? Occasionally, once in a long, long time, it happens that the compiler is wrong, and very rarely that the actual CPU is wrong, right? But we humans are extremely error-prone, right? And we should admit it, and we shouldn't punish our kids for making errors when they are doing calculations like these. This is normal for us to make errors, okay? Let's accept it. Computers don't make these errors, and computers should do these things. We have calculators. We can calculate always stuff, right? We don't need that. And finally, the language. There's this language barrier, okay? And I think, of course, computers understand machine language, right? And we used to program in machine language in the very, very beginning, switches, zeros, ones, and so on. Very quickly, we learned we humans are not very good. Computers don't mind. Okay, zeros, ones, great. But we humans do mind. It's very difficult for us to program using zeros and ones. So we come up with higher and higher level languages to program computers. But ultimately, and that's my main point, is that ultimately the language that's most human to talk about ideas is the language of mathematics. And the reasons why we are not constantly using mathematics when we are talking about programming is because of that, because of this multiplication that they forced on us, that they taught us mathematics in the wrong way. And category theory is a branch of mathematics that doesn't look like this. It looks much nicer. It doesn't talk about numbers and doesn't talk about making stupid mistakes and algorithms and so on. It talks about ideas. And that's much more human-like than dealing with numbers and bits. So I think the reason it's sometimes easier for us to think like a machine, for programmers to think like a machine than use mathematics, is because of this unfortunate bias. So when we talk to computers, right, we use computer languages. And the important thing is, when we program, we have to understand the meaning of the program that we are writing, right? That's called semantics. So you're programming a language, and the language has to have some kind of semantics. What does it mean to say for n equals 1 and less than n plus plus, and so on, right? Then what's the semantics of this? So there are several approaches to defining semantics of languages. One is this operational semantics, when we say, you know, if you are in this state and you do this, then the next state will be this. And then if you apply this, then the next state will be this, okay? I think this kind of operational semantics is very computer-oriented, not human-oriented, right? So the other approach is denotational semantics. In denotational semantics, we say this program has meaning because it can be translated into another language that we humans understand much better. And the perfect language for this is the language of mathematics. So in most cases, denotational semantics means your program actually has a meaning as a piece of mathematics, like a proof, like a theorem, you know, like an operation in mathematics, or declaration, definition, you know, right? And when we are using operational semantics and we are writing a program, how do we understand what this program does? Mostly, we are running this like imaginary machine in our minds, and we are going like, this statement will do this, then this statement will do this. We'll change these variables, so I have to keep in mind which variables are, right? I mean, this is some people are very good at this, and some people are very bad at this. I am bad at this, okay? And I've seen people who like think more like machines, and they can do very quick programming, you know, and so but I think ultimately, you know, none of us is as good as a computer at that kind of game, right? So we shouldn't try to beat the computer at their games. We should try the computers to beat us at our games. Let's see them compete with us, right? Not the other way around. And math is this ancient language, thousands of years, right? And it was developed long, long before we had computers. It was developed by humans for humans to communicate about ideas, right? That's very important. So, you know, we cannot dismiss math so easily as a language. So let's talk about functional programming. Functional programming, and I want to like start explaining a little bit of this mathematical semantics, right? So in functional programming, we deal with types and functions, right? And like the simplest mathematical model for a type is that a type is a set of values. So set theory, okay? So that's a branch of mathematics that talks about sets, okay? Fine. Functions in this model correspond to functions between sets. So it's like, you know, give me this element of a set, I'll give you that element of a set. And in this kind of theoretical mathematical view, really we are not talking about how the function is evaluated. This is what computers do. They evaluate this function. But we first concentrate on the definition of a function, like what is actually happening. If I give you this argument, what will you return? Right? In mathematics, we don't really deal with time. Like how long will it take to calculate this value? It doesn't matter. First, we have to start by understanding this value corresponds to this value. So function is just a mapping of values to values between different types in general, right? But this is really, now mathematicians, that's a funny thing. And mathematicians also consider set theory as sort of an assembly language of mathematics. Mathematics also has these levels of abstraction, right? It's building higher and higher levels of abstraction. And set theory turns out to be this really low-level assembly language of mathematics. And mathematicians recently try to avoid using set theory so much as they used to. Like there are new branches of mathematics like homotopy type theory and category theory that try to avoid using the assembly language. So even they are going a little bit higher. So I think we could also go a little bit higher and think of program semantics in terms of category theory rather than sets. And sets form a category. That's fine, you know, and sort of like a lot of our intuitions about category comes from set theory. So for most purposes, like we think about an example in set theory and we sort of try to recast it into categorical terms for programming, okay? So like in a categorical view, category theory simplifies these things tremendously because it says there are only two things, objects and morphisms or arrows between objects. That's it. And it doesn't even specify what these objects are, what these arrows are. The mapping between category theory and programming is just this. Functions that we use in programming. So here function meaning what we program, right, in a language. These are the arrows between objects. And the objects are types. So like you have integer type, you know, tree type, list type, whatever type you are using. Okay? These are your objects. But the important difference between the set theoretical view and categorical view is that it's a change of perspective. In set theoretical view, you define properties of sets by talking about elements of sets. Okay? In categorical view, you shrink the whole set to a point. You say, I cannot look at the structure of the set. It's forbidden. So it's like, we know in functional programming, there are certain things that are forbidden, right? Like you are not supposed to modify a variable, right? And that forces us to change perspective, right? We come up with these persistent data structures and so on, right? Because we are forbidden to do certain things. So if you switch this perspective that you are forbidden to talk about elements of sets or talking about values, you know, then suddenly you have to like rethink everything and say, so how do I describe different kinds of sets? You describe them by their interaction with other sets, which in category theory means arrows. So you can describe properties of objects by talking about arrows, the arrows that are incoming into these objects and the arrows that are outgoing from these objects, okay? And that's a very interesting way of looking at things. So it's like, tell me who your friends are and I'll tell you who you are, right? Exactly this way. So instead of interviewing you, I'm just interviewing your friends and I can learn much more about you, right? But in principle, we just want to be able to express the same things we can express using elements of sets as we can do with arrows. Okay, so this is like a very quick recap of the definition of a category. You've heard it several times, and Daniela talked about what the category is. So objects and arrows, and in parentheses I say what's your model for this? Like, oh, let's think about types and functions in programming, right? But in categories are all kinds of different categories, right? But that's the one important for us. I'll talk about another category that's not exactly types and functions later, the functor category. The most important thing about arrows is that they compose. This is why category theory is all about composition. There's nothing more in category theory but this composition. If two arrows match end to end from A to B and B to C, then you can go from A to C. That's it, right? And we want these properties. We want associativity of composition. So composition here is this little circle. That's how mathematicians notate it. In Haskell, it's a dot. And I guess in Scala, it's compose, right? And there has to be an identity. Every object has to have an arrow that goes from the object back to itself. And sort of, you can say this is an arrow that does nothing. But you cannot say it does nothing because an arrow doesn't do anything to an object because objects don't have structure. They are just these points, right? So doing nothing that doesn't even make sense. But you can say that if you compose it with something else, then it does nothing to composition. So you compose ID with F, you get back F. You compose F with ID, you get back F. So composing with ID doesn't change anything. OK, so now let's get to work. Okay? We want to define some very simple things that we know from set theory or from type theory from programming, some data types, okay, using purely categorical language. So the first data type is void. This is not a type that you would use normally every day. It corresponds to an empty set. So what kind of type it is? There's not much that you can do with it, right? But it's interesting as like a boundary case, right? So from point of view of set theory, we are describing an empty set, no elements, okay? But in category theory, since we cannot talk about the elements, we don't know what it means, no elements, right? We don't know what elements are. So we have to define it using arrows. And defining something using arrows in category theory means saying something universal, meaning you have to tell me about the relationship of this object with the rest of the universe, with every other object in the category. Mathematicians are not afraid of infinities. It's like you have infinitely many types, possible types, right? We are talking not only about the types that you use from day to day in programming. We are talking about all possible types that you can invent and describe, right? Lists, queues, trees, whatever, right? All these types. So there is this universal property, and in category theory, the object that has this property is called the initial object in a category. Not every category has an initial object. Category of sets has an initial object, which is an empty set. Okay? And the universal property of this object is that it has an arrow going to every single other object in the category. Moreover, there is only one such arrow for every object. So, like, you pick one object, this one, okay? There has to be a single arrow going from my initial object to this object. Not 2 arrows, not 3 arrows, not 0 arrows, 1, okay? And this is a translation to Scala that was done by a friend of mine. Because I wrote it in Haskell and he translated. So when we are defining data types in these categorical terms, it's usually a definition consists of two parts. Because we have to say about the arrows that are coming into the object and something about the arrows that are outgoing from this object. So the arrows that are coming to an object, we call them constructors, right? Because like you take some type or a bunch of types and you construct my object, right? So these arrows are functions, right? So you have a function that takes a bunch of objects and produces my object. That's a constructor. So incoming arrows are constructors. And in mathematics, it's called introduction rule. Introduction rule corresponds to what we say a constructor, right? So there is no possibility of constructing an empty set. What does it mean? What does it mean to construct an empty set? It means to write a function that would return an element of an empty set. Okay? In set theoretical, there's no way you can write a function that would return an element of an empty set because an empty set has no elements, right? So there is no introduction for type void. The outgoing arrows, okay, this is called the elimination. Okay, so like if you give me an object of type void, what can I do with it? Elimination means eliminate the object, well, in a sense, by transforming it in something else, right? So I need to know what kind of arrows are outgoing from this object. And for the initial object, you know, all we know is that there is a single arrow to any other object. So this is what you would say in Scala. There is a unique function for every type A. There's a function called absurd. So it's a polymorphic function, right? Because it works for any type. It's a polymorphic function, absurd, that takes a void and produces an A. How does it do it? Well, don't ask me how it does it. Just give me an element of void, and I'll give you an element of A. OK? So that's a kind of tricky thing, yes?
Sorry, short question. What do you mean by including self then? So if void doesn't have a constructor, including self?
Including self, it means every object in a category theory has to have the identity arrow, including this one. So it has an identity arrow. An identity arrow is an example of a function that takes a void and returns a void. Okay? Well, so this is like, yeah, I mean, if you give me a void, I'll return you a void. And I can even implement this function. Here's an element of void. I'm returning it back to you. Yes?
But if it doesn't have inbound arrows, how is it possible?
I didn't say it doesn't have inbound arrows.
Okay.
I didn't say that. I said it has a unique outgoing arrow. Didn't say anything about inbound arrows.
Is the method absurd? Is it a synonym for a method that don't take an argument as input? Is it a same thing or not?
Well, it's. I mean, from the point of view of mathematics, right? Like if you try to do it in set theory, okay. So how many functions are there from an empty set to another set? There's only one, okay. It doesn't matter what it does, right? Because you can never call it. Okay? I mean, this is typical mathematical thinking, but there's an interesting thing about this because there's a one-to-one correspondence between category theory and logic and type theory. So logically, this corresponds to the statement that from falsehood, void corresponds to falsehood in logic. Okay, so from falsehood you can derive anything, right? So this is why this function is called absurd. Okay, next one. Next one is a little bit more useful. It's called unit. Okay, the type is called unit. In set theory, this corresponds to a singleton set, a set that has only one element. Okay? So this is type unit also in Scala, right? There is a type unit. And it has a single element. I don't know, is that what you call this element? Yeah? Okay. Just like in Haskell. In Haskell, this type also is called bracket, right? So this is like the opposite of the initial object. It's called a terminal object. And by opposite, I mean it's dual. So actually, in category theory, you have this duality. Like whatever definition you come up with, you can just invert all the arrows and you get something else for free. So here we are just inverting the arrows. And we're saying, OK, the universal property of a terminal object is that there is a unique arrow from any type to it, okay, from any object, from any type. So now this guy will have an introduction rule, right, which says that for any type A, you can produce a unit. How is this function implemented? It just ignores the input, right, and just returns this unit, because it can always produce the unit, the element of the singleton set called the unit, right? So this is very easy to implement. It's like we can implement all these functions, right? That's great. The elimination rule, and here we can clearly see that, you know, I'm talking about incoming arrows. It doesn't mean that there are no outgoing arrows. In fact, there are lots of outgoing arrows from it. The elimination rule is that if you have a unit, you can have a function to any other type. And in fact, you have many functions, depending on the type. What does a function from unit to a type do? It picks one element from this type, right? So if we give me a unit, I can define a function to integer that returns 7. I can define another function from unit to integer that returns 42. And so on, right? So this is actually a pretty useful thing because we are not supposed to talk about elements, but if we want to pick an element from a type, we can always cheat. We can say, OK, I cannot pick an element, but I can say that there is a morphism or arrow from unit to this. Okay, so instead of picking element, you pick a morphism. A morphism is the same as arrow. Okay. Okay, now for something really interesting, product. Okay, so product in set theory, this is just Cartesian product or a set of pairs. So you have two types, right, and you produce a pair type from these two types, right? So the universal construction for this thing is kind of interesting because, like, what is the property in terms of arrows of a product? The only thing we can say that there have to be two arrows from a product, one going to the type A and one going to type B. If you have a product of A and B, right? These are called projections, right? Like if you have a pair of integer and bool, then you can project an integer. And I think this function called _1 in Scala. Yeah? OK. Good translation. And there's _2. So we know, but what else can we say about a product that would identify it from many other possible objects in the universe, right? Well, so we say, OK, well, let's try some other object. Let's say C, OK? Suppose that C has these two projections also. So we know that a candidate for a product has to have these two projections, right? And the only thing we know about these projections is that there are arrows. So there is an arrow F to A, and there's an arrow G to B. Okay? So out of all these candidates, we can pick the best one. So look at all possible candidates, all possible types that have a projection on A and B. Pick the best one. How do we pick the best one? Okay, the best one is the one that for any other type, there's a unique arrow going to this type. Okay? So like, for instance, you come up with a candidate that say, a triple A, B, and C, okay? And I say, well, the pair AB is better than triple ABC. Why? Because there is a unique function H that just picks the pair from the triple, right? Just discards C and picks AB. And this function has this property and that we can express in terms of composability, that this arrow composed with this arrow gives me this arrow. And this arrow composed with this arrow gives me this arrow. So if I go through H and then project the first component, it's the same as going through F. So this is a universal property. From all the objects, I pick the best one that has this property that any other is decomposable into it. Okay? And this might seem like really a crazy way of defining things, because like, how would you write a program to do this? Well, let me go write a big loop in which I go over all possible types in my type system, right? It's crazy, right? There are infinitely many of them. And then for each of these types, see if I have arrows going to A and B, right? And then from all these, see if I have a unique arrow going to AB. And if this is true, then I had my product. If it's not true, then I try a different candidate, and so on forever. You know? But there is no time in mathematics. Yeah, I think I'm not even going to get through half of my presentation. Okay, so here it is written, you know, F is from C to A, G is from C to B, and H can be defined, you know, like as programmers, we can define this H, you know, F acting on C paired with G acting on C. That's the solution of this problem, right? And of course, I have to say, what is the introduction and what is the elimination? The introduction, you have to have, in order to produce a pair, you have to have A, and you have to have an element of A, and you have to have an element of B. You need both of them to create a pair, right? So that's the constructor of a pair, very simple. The elimination rule is these two arrows from A to B. So if you give me a pair, what can I do with a pair? Well, I can project it. I can extract the first part or the second part. That's all I can do. And then I can do with this stuff more, you know, more interesting things. But I always start by projecting. And this defines all the product types. This is why they are called product types, because they come from a product. Things like pairs, tuples, records, and so on, right? And of course, there's a dual to it, a sum type. Okay, now you will understand why these things are called sum types. They are called also a coproduct. In category theory, they are called a coproduct because they are dual to a product. And it's just the same picture, but I took the upside down and reversed all the arrows. Okay? So a sum type, an example is either A and B. Okay, that's like the simplest sum type of two types. instead of having these projections, it has injections, left and right. So left takes A and produces either A and B, right? It doesn't need a B. It's enough that it has an A. Or if you have B, you can produce either an AB, and you don't need A, right? So there are two ways of constructing it. Now again, universal construction says either A and B is like the best of these guys that have these two injections. Anything else that has these two injections will factorize through some unique H. Okay? So here's this factorization. Like, how can you define H, from the type either A, B, if you have these two injections, F and G. So F and G here are these two injections, right? These, and here I'm defining H from either A, B to my type C, right? And I just do case analysis. If it's left, then FA. If it's right, then GB. And I got it. Right? And introduction, I can introduce the type either A and B if I have A or if I have B. There are two ways of introducing it. The elimination is just by pattern matching, left, right. And this is, in programming, it's usually called tagged unions, right? In Scala, you have different name for it. But you use the term sum types, right? So this is where they come from. They come from sum types, okay? Monoidal category. Wonderful thing, huh? Very simple. So I told you already everything about this monoidal category. I told you it's a category in which you have both products. For every two elements, you can create a product. And for every two elements, you can create a sum type. Okay? So why is it called monoidal? Okay, let me explain why it's called monoidal. Because this product kind of looks like multiplication. And monoid is something that has this multiplication, essentially, or addition. It's like a simple arithmetic. So it has this operation that operates on two things and produces one thing, right? So so this is a monoid in types. So given two types, I can multiply them by creating a product type, right? A pair type. So that's my multiplication. Now, in order for this to be a monoid, it has to be associative. So like if I have three types, right, I can pair them differently. I can pair B with C and then pair it with A, or I can pair A and B and then pair it with C. This is not exactly the same type, like the type checker would reject this in a program. However, these two types are isomorphic, meaning there is a function that takes this type to this type, and there's an inverse function that takes this type to this type. It just rearranges stuff. That's very simple. So up to isomorphism, this is associative. And the other thing that the monoid has to have is this has to have this unit. Something that if you multiply by unit, you don't change anything, right? And the unit, in case of these types, is the unit type, actually. So this is why it's called unit type, right? Because if you take a pair of unit and A, it is equivalent to A. You're not adding any more information to A by pairing it with a unit, right? It's like a redundant thing, okay? Also up to isomorphism. So this is why it's called a monoid. So we have a monoidal category at our disposal. And also, the coproduct, the sum types, also form a monoid, separate monoid. Here's the associativity for either. And here's the unit. The unit for either, and this is where void comes back, right? This type void is a unit. Because if you take either void or A, it definitely contains A. Why do I know this? Because try to create, from void. The void has no element, so it will never be called. So this one injection just doesn't exist. The injection that will inject a void to a sum type. So it always has to have an A. The only way you can construct this by providing an A, and you can extract this A. So it's the isomorphic. So this is why we have this beautiful algebra of types. Okay, we have a monoid with respect to product. We have a monoid with respect to sum. They actually interact together very nicely. So we have like a bicartesian monoidal category, something like this beautiful name that mathematicians give it. But this is really what we need for programming. We need a monoidal category because we have to have sum types and we have to have product types, right? We also have to have function types, and that will be like the second part of my talk. And I think I'm just going to stop it here because
Next talk is at 5. So if you want to, you can go. If the crowd is okay, of course.
Is there enough tape? Is there enough tape for to type it? So how about if we make like a 1-minute break so that people who don't want to listen can leave, and I will not be watching, okay? Okay, so here's the way we can use this algebra of types to create, essentially from this point all, we can create all types with just these tools. Okay, this will be kind of awkward. For instance, the type Boolean, right? It's nice to have a Boolean type. A Boolean type is just either unit or unit. It means you can create it as a left thing or a right thing, and it has no other information other than whether it's left or right. And we call the left thing true, for instance, and the right thing false. That's it, the sum type. It can either be true or false, right? So here's like the sealed straight bool. Okay, so this is how you do sum types in Scala, right? Type natural. That's like you would have to do infinitely many. But this is type natural number is either 1 or 2 or 3 or 4 and so on. So it is a sum type. So essentially having sum types, and if you apply it infinitely many times, you'll get natural numbers. Okay, this is a very awkward definition. There are better definitions than that, right? But just to show you the idea, right? The option type, right? The maybe type, the option type. A little bit more interesting. It's a sum type. It's either of unit and A. So it is a polymorphic type, parameterized type by some type A, right? So you can either construct by providing unit, which you can always do, and that's the nothing part in Haskell. What do you call it in Scala? None. Okay, so none, that corresponds to none. And this corresponds to, what do you call it? Sum. Okay, none, sum. Nothing, just in Haskell. Same thing, right? Then you can go into recursive types. You can define a list. List is a sum of two things. Unit here, that signifies empty list. You can construct an empty list, right? Always, right? And contains no information. So you can construct it from unit. Unit you always have at your disposal because units are just like everywhere. You just pull them from the air and you create a list using unit, and that's an empty list. Or you can create it from a product here, right, of A, which will serve as the head of the list, and a whole other list, which is the tail of the list, right? So here we have a sum and a product together, and it's recursive, right? And this is how you could express it, okay? So this is like the skeleton of a whole type system. Everything else is just syntactic sugar on top of this. So that's very interesting to know, right? Okay, so now you've heard the word functor so many times today, right? And yesterday. Okay, so let me just like introduce the functor categorically. So in general, a functor is a mapping between categories. So mathematicians are always interested in how things that have a certain structure relate to another thing that has a similar structure, right? And a functor, in this case, takes one category and embeds its structure into another category. So it's a mapping from category to category. So if it's mapping a category, and the category is nothing else but objects and arrows, so naturally it has to map objects and arrows. So it maps objects to objects and arrows to arrows, right? And because it has to preserve the structure, what does it mean, structure? It means that if you have an object A and an object B, okay, so A goes into FA, that's an object FA, this is an object FB, right? If there is an arrow between A and B, then this arrow has to be mapped into another arrow, right? But it cannot be an arbitrary arrow anywhere else, right? It better be an arrow that connects F of A to F of B, right? Because, if these things are connected in this category, they must be connected in this category as well, okay? A functor may do things like collapse two objects into one. It can collapse multiple arrows into one, and so on. But as long as you have a connection in one category, it will preserve this connection. And it will also preserve the unit arrows, and it will preserve the composition of arrows, okay? So how does this translate into programming? Well, so first of all, in mathematics, the most general functor goes from one category to another category. In programming, most of the functors will go from the same category to the same category. They are called endo-functors. Endo means inside, like endoscopy, Yeah, so we have a functor that goes within the category. So like it takes a type A and maps it into a type list of A, okay? So it takes a type integer, maps it to list of integer. It's mapping between types. It's not, this is a very important thing. Many people get confused because of this. It's not mapping of elements of these sets. It just maps the whole set into the whole set. It's like, say, here's an integer set, or integer type, maps it into a list of integer type to type. Like a parametric type, right? A type constructor, right? Okay, so type constructor. So the type constructor part of it is that this F with a bracket in Scala, right? So that's a type constructor. It takes a type and produces a type F of A. Takes A and produces F of A. So this is the part of acting on objects, the blue arrows. And we have to separately define how it acts on arrows. So it takes an arrow, F. So that's this arrow, F. This arrow goes from A to B, right? From A to B, okay? And maps it into an arrow that takes F of A, this guy, and returns F of B, this guy, okay? So like if you draw a picture, this is really very simple, right? So it takes this arrow and maps it into this arrow. And you have to provide these functions. Like for every functor, you have to provide. Like part of the definition of a functor is how does it act on arrows, right? And maybe there are sometimes functors that have different actions on arrows, the same action on object, but differ by acting on arrows. Okay. So I guess this is okay. I think you guys call it map, not fmap. Haskell calls it fmap. So for historical reasons, really not. So this is how it acts on lists, right? But you've seen this before. So why am I talking about functors? And now I have to introduce adjunctions between functors. I have to introduce adjunctions between functors because there is one extremely important example of an adjunction that's very useful in programming, especially functional programming. So little motivation, right? You know what types are. So I told you about all these types. They are objects. Separately, I said we have arrows. They correspond to functions. Okay? But you know that, like when I say from A to B, I mean a type of a function, right? A type of a function. But we said types are objects. And this is an arrow, right? So how is this connected? So you have to have an object inside the category of types that corresponds to the set of arrows between objects A and B. So for every pair of objects A and B, there is a set of arrows between them, but there has to be also an object, separate objects, that represents this set of arrows, right? And that's called the type of function type. Not every category will have this, but the category that we are interested in which we can program, must have this object for every pair of A and B. Okay, and this object can be introduced by another universal construction I'll show you in a moment. But the easiest way of introducing it is through an adjunction of two functors, in particular two endofunctors that we are interested. So an adjunction is not one functor, but a pair of functor. One functor adjoined to the other functor. Okay? So one functor goes from one category, from this category to this category, and there's another functor going this way. Okay? So like if you have two functors going in the opposite directions, you might say, okay, like if one is the inverse of another, that means that these two categories look the same, right? There is like an isomorphism of categories. But it's much more interesting if these are not inverses of each other, but they act in a very interesting way on arrows. Okay? So we say that the functor f is left adjoined to the functor u if you draw the set of arrows from fa to b and the set of arrows from a to ub, they are isomorphic. Having isomorphic set of arrows tells us about how these two objects are related, right? They are related in a particular way. If they have the same set of arrows going between them, right, it means that their relationship is very similar. And you can think of this as like you are preparing an argument for a function, using functor f. And here you are modifying the output of a function by applying functor u. So if you prepare arguments to functions or you modify the output of functions, you get this isomorphism between these two. Okay? And when you hear this first time, it's really like kind of weird. Like, why is this so interesting? So I'll give you one example, and there are many, many interesting examples. But I'll give you one example that like pops out immediately. So let's pick the functor f acting on A. It pairs it with C. Okay, so I take the type A and I pair it with C. I get a pair type. So that's one functor. The other functor is acting on B. It creates a type of function from C to B. Okay? Nothing yet, right? It's like, oh, okay. Well, all right. Now let me write this isomorphism between these. So like if I prepare my argument by pairing it with C, okay, and I have a function on arrow from A comma C to B, this is equivalent, isomorphic, to all these functions that take A without any preparation, but modify the argument B by putting this as an output of a function that takes C. Okay? Now, if you look at it, this is called currying, right? Currying. A function that takes a pair is equivalent to a function that takes one element and returns another function that takes the second one. Okay? So this is how currying arises from an adjunction. Right? This is this adjunction. Oh, this is a general adjunction, right? This is this particular adjunction. And in category theory, this function type, this C to B, because you can take this as a definition of the function object, because this is a type from functions from C to B. You can say this, if you have in your category pairing or product, then you may, if you have this adjunction, you will be able to define what it means to have a function type. Right? And the category in which this is defined is called closed. So taking together, we have a Cartesian closed category. Cartesian because it has a Cartesian product. Closed because it has a function type. And we are operating a Cartesian closed category when we are doing programming. Right? So next time somebody tells you about Cartesian closed categories, you know, oh yeah, this is what we use in our everyday programming. This is what, yeah, this is our bread and butter. In mathematics, this is called an exponential, A to B. Function type from B to A is called A to the power of B. And it actually, I'm not going to go into it, but actually, like if you look at it as an exponential, and combine it with multiplication being product type, sum type, using either and exponential, you can like write all these identities from high school, like A plus B to the power of C is A to the power of B plus, and so on. All these identities actually work on types, which is, on one level, it's a weird thing, right? On another level, you see the repetition of the same patterns in mathematics all the time. And that's an interesting thing to like, think about in your free time. So I'll show you just this diagram. Function types can be defined using universal construction. Right? This is like the diagram that it's a little bit more complicated than defining a product, but it can be done. Okay? And of course, we can say, what's the introduction and elimination? The introduction of function is called lambda. Okay? So if you have an object of type A, and you have an expression of type B, then lambda x e of x is of the type A to B. Okay. And elimination is called eval. So you eliminate a function by providing an argument and getting the result. Okay, so I'll have to speed up now. Natural transformations are extremely important. We know them as polymorphic functions, okay? In category theory, they are just mappings between functors. So if you have two functors, f and g, you pick an object A, and you map it to fa, and you can map it to ga. A natural transformation is when you pick these arrows. For every FAGA, you pick one arrow. So you pick a function that depends on A, right? You keep changing A, you get different functions. So it's a polymorphic function. It's a polymorphic function whose argument is a functorial and whose result is functorial. So here's an example of something like this. You take a list and you produce an option, right? Did I rewrite it? No, this is, yeah. Okay, none, some. Okay, yeah. It returns an option, right? Why is it important to have natural transformations? Because now I can say, and this is like a typical thing in category theory. Okay, I have functors, and I have natural transformations which transform one functor to another. Okay. Are these arrows between functors? Maybe I have a category, right? Like what if functors are objects, and natural transformations would be arrows between these objects? Okay. What do I have to show? I have to show, if I want to have a category, I would have to show that there is a composition. And of course, there is a composition of these arrows, because if I have another functor, h, I'll just compose these two, and I get a third one, right? There is an identity, and of course, there is associativity, right? Associativity and identity. So that works fine, right? So I can construct something called a functor category in which objects are functors and arrows are natural transformations. So this is an example of a category that's not slightly different than what we were talking about before, right? But it is a very important category, a functor category. Now, in our case, we talk about endofunctors, and endofunctors also, being functors, form a category, right? So they form a category. It's called, that's how mathematicians write it. It's a category of functors from C to C, okay? So the final minute, the Oneida embedding, okay? The Oneida embedding. So this is the kind of thinking that can break your brain a little bit, right? but it shows you the power of category theory. This is like, because there is this notion that we have replaced contents of objects. We replace it with arrows. Like we can say everything we can say about the object can be said using arrows, right? Objects shrunk to a point, and everything, all its properties are expressed using arrows. So the next step would be to say, well, instead of talking about an object, why don't I talk about all the arrows that are, let's say, impinging on this object, okay? Like, if I take the totality of arrows in my category that end in this object, do they contain exactly the same information as the object itself? It's like, right? Can I replace this object by just talking about the totality of arrows that come to this object? And the answer is yes. And it's called the Oneida embedding. Okay? So let me go through like steps, right? So first of all, how do I even define the totality of arrows coming to an object? Well, I'll start with so I'm talking about object A. That's my object, okay? Let me pick another object, X, and have a totality of arrows from X to A to begin with. I have to start somewhere, right? So let me take these arrows. What do they form a set. They form a set of arrows. Set of arrows from X to A, okay? But this is just one X. If I want to talk about totality of arrows that go to A, I have to vary X. I have to go to every possible X in my category, right? So if I start varying X, then I get different sets here. So this is for X. I pick Y. There will be from Y to A, and so on. So I end up with something that is like a mapping of X, when I vary X, to sets. Sets are objects in the category of set. Okay? So I have a mapping that goes from X to A for a fixed A. And this mapping, I define this mapping for objects, for X's, right? This mapping can be extended also to arrows, which means that it's really a functor. This is a functor if you vary X. It's called a contravariant functor because it acts weirdly on arrows, like the opposite of the arrows. But it's a functor, and it's a functor from this category C to the category set. Okay? So now, for every object A, I get a functor from C to set. Okay? Keep this in mind. From every A, I have a functor from C to set. It just takes an X and puts it into XA. So now if I start varying A on top of this, okay, then I have a mapping that takes an A and creates a functor from C to set. Okay? So this is the functor category from C to set. Here's my X, here's my A. I'm varying A to B, okay? So for every object A, I have a functor, right, that takes these arrows and puts it here, right? So I have a mapping that embeds an object from category C into the functor category. And now if I have a mapping of objects from one category, C, to another category, which is a functor category, is this mapping a functor? Turns out this mapping is a functor too. Okay? And moreover, its action on arrows, so here's an arrow from A to B, its action of arrows, well, so if its action on arrows would have to be a natural transformation because arrows in this category are natural transformations. So there's a mapping from these arrows to these arrows. These are just functions. These are natural transformations, right? So this is a function from A to B. It's mapped into this natural transformation from this functor to this functor. Okay? When I vary X, this is a functor. Okay? And the Monoidal lemma says this mapping goes both ways. It's actually an isomorphism, which means that this whole category C can be embedded in the category of functors, which is called a fully faithful embedding, meaning it takes all arrows and nothing more and maps them to all two arrows here. So if you map A to this functor, B to this functor, all arrows from A to B go into natural transformations from this functor to this functor, and nothing more is there. So like you can take all natural transformations, they will correspond to arrows here, right? So you have like a perfect picture of this whole category embedded in this category of functors. Okay, and I think this is a good point to end. Okay, thank you.